the final talk of our meeting, which will be given by Andrew King, who is the Director of Performance Research at D-Wave. And D-Wave, everybody knows, has been producing all these wonderful quantum computers, which have large number of qubits, which are very special. So we will hear the talk on what a computational performance advantage means for the future of practical quantum computing. Andrew King, the screen is yours. Welcome.
Thank you very much. So thank you to the organizers. It's nice to be here, wherever here is. I'm definitely missing the travel aspect of going to conferences. It would be lovely to visit Poland. I'm going to talk about some recent results that we've seen performing quantum simulation tasks with D-Wave quantum annealing processors and what they mean in the context of practical quantum computing. So it's a very interesting time for quantum computing as an industry. We've seen a lot of results coming out of a lot of different groups, and people are getting really excited about it. So there's a lot of interesting work, and there's also a lot of hype. And I'm going to try to stick to the interesting work. So what we have at D-Wave is a quantum annealing processor, and I'll get into what quantum annealing is in a couple of slides. That little black box in that circle, that's actually about 3 meters by 3 meters by 3 meters. And it's a magnetically shielded room that holds a big refrigerator that keeps things at about 10 millikelvin. It's got a rack of classical co-processing on the front of it, and it's big enough to hold a few engineers and a quantum processor. So I had something that was approximately the same size. So that the D-Wave chip is actually about that big. It's about 1 centimeter squared. And the current Advantage processors have 5,000 qubits, over 5,000 qubits. So in terms of practical applications, we've seen some really interesting uptake by people in industry doing proof of concept industrial applications. Just a few examples. Menton is a company that does protein discovery, de novo protein discovery, and they've used D-Wave's processors. Save On Foods is a large grocery chain similar to Tesco or Aldi. And they've done some interesting applications with scheduling, logistics, operations research, that kind of thing. Volkswagen is a company everybody knows, of course. They've done some applications on traffic routing and paint shop scheduling. So you have a set of cars that need to be painted. It costs a bunch of time and therefore a bunch of money to change all the nozzles on the tools when you want to change colors. So you do this as rarely as you can. And then that becomes a combinatorial optimization problem, similar to job shop scheduling types of problems. And then OTI Lumionics is a company that makes materials for screen displays, and they've used D-Wave processors in an effort to discover new materials. But I'm not going to talk about any of these applications. I'm going to get very, very into what's going on actually in the processor rather than the overall application stack. So under the hood, I'm actually a computer scientist by background. My original research was in graph theory and algorithms and things like that. And I've sort of drifted over towards physics more and more as I've been at D-Wave for 8 years now. But the model of computation is like the Icing model. So probably it's fairly widely known, the Icing model. This is the orange part of this Hamiltonian. And a Hamiltonian, you can think of this as just a cost function or an objective function that needs to be minimized if you're not with a background in physics. So h of s is the cost function of a spin configuration or a variable state s, which is a vector. So the classical Icing Hamiltonian is actually just a set of linear constraints or linear penalties and quadratic penalties. They make variables want to be similar or different or biased in one direction or the other. And minimizing the energy or the cost of a classical Icing Hamiltonian is an NP-complete problem. So if you have a background in computer science, you know this is intractable, and therefore you can solve all sorts of interesting and difficult problems with it. What we do is we add quantum fluctuations, and this is not an idea that started with D-Wave. It was an idea that started in the lab where people had a spin glass sample, and they were trying to kind of see if they could anneal it to a low energy state faster than reducing the temperature gradually. So they actually found that instead of reducing temperature, they could reduce an external magnetic field that was transverse to the effective spins. And they found that this optimized the sample more easily. So what we do is a programmable version of that. So you can see in the bottom left, we have the annealing schedule. And so the computation runs from 0 to 1. And this is just moving forward in time. And we've got two parameters. J of S over T is the energy of the classical Icing Hamiltonian divided by temperature. And gamma of S over T is the quantum fluctuations. So in the beginning of the computation, we're totally dominated by quantum effects. So the system is completely quantum, but it's also completely disordered and therefore not interesting at all. At the end of the anneal, we have slow dynamics, and we have a very large classical Icing Hamiltonian compared to the temperature. And so if we can find a low energy state of that, then we're in really good shape. But what happens in the middle of the anneal, near the quantum critical point, is the most interesting. So this is where you have a combination of quantum and classical effects, hopefully finding a good answer to your question quickly. Now, the applications that I'm going to talk about are related to programmable quantum magnets, and shown in the bottom right is an example of a cylindrical programmable quantum magnet that we studied in detail in a couple of papers. Now, the blue lines are couplers between two qubits. All the white dots are qubits. The blue lines join two qubits, and they say these qubits should be the same. They're ferromagnetic couplings, so they make these spins want to be the same. And the red couplers are antiferromagnetic, so they repulse these two spins from each other in terms of their spin value, which is up or down usually. And so we have this competition between terms that is difficult to satisfy or impossible to satisfy all of the terms simultaneously. This is called geometrical frustration. And it gives rise to a lot of exotic physics that we studied in these applications. So we can program a variety of quantum magnets into the system, and I'm going to give you 3 examples and then get into a larger amount of detail in the third one, which is actually the one that I'm showing right now. But the first application of this type was a 3-dimensional spin glass. And this was the first result that was really realizing Richard Feynman's vision of programming quantum matter as a method of studying quantum matter. So what we have here is these couplers, these spin-spin interactions are selected randomly. So this is thought of as doping. We can have a ferromagnet, and you flip a certain number of the couplers to be antiferromagnetic, and this leads to a spin glass as long as you flip enough of them. So 3-dimensional spin glasses, coming from a complexity theory point of view, these are paradigmatic hard optimization problems because they're not planar and they have very complicated energy landscapes, and it's hard to find the optimal state for these systems. And when you add quantum fluctuations, you get a different phase diagram than you do in the classical case. So this work of Richard Harris et al. At D-Wave was published in Science in 2018 and essentially traced out the phase diagram of this quantum matter in such a way that gave us a good idea of what was going on in the programmable material. But this paper didn't consider the computational efficiency of the simulation. Another more recent paper, this was just published last week in Science, and this is another matter by design. So there's a whole field of study called artificial spin ice, and in this you make a frustrated system, and you have magnetic moments. Usually you lithograph them as nanomagnets in a very thin layer of metal, and you can tune the geometries of these nanomagnets, and based on the way that you tune them, you get different behaviors coming out of the system. So we thought, well, we don't want to fabricate and tune the geometries a bunch of times to make this artificial spin ice. But what we can do is we can program it into the qubits of the D-Wave processor. And so we did that, and we could do a couple of things that were not possible in previous implementations of artificial spin ice. So one thing that we can do is we can pin individual qubits to a desired value. This is something that's very difficult in other types of experiments. And by pinning these spins on the boundary, we can actually trap emergent flux into the system. So you can see all these arrows going in and out of the boundary of the lattice in this picture. And if the arrows going in are not equal in number to the arrows pointing out, then you have non-zero flux. And then you apply Gauss's law, which is something that physicists learn in undergrad. And you know that you're going to have a charge in this system because you have non-zero flux. And this charge is actually a magnetic monopole. So it shows up as an emergent magnetic monopole. This is a quasi-particle, and we can actually watch this quasi-particle move around, and we can watch two of them interact with one another, which was never possible with previous realizations of artificial spin ice. But again, also in this experiment, we did not study the efficiency of the simulation. So going back a few years, in 2018, we published a paper on the system that I showed you before. It's a geometrically frustrated two-dimensional system with cylindrical boundary conditions. And this is a system that is really interesting because it has a completely different kind of order in the classical system than it does in the quantum system. So in the classical system, it's a spin liquid at zero temperature. And once you add quantum fluctuations, you see a phenomenon called order by disorder. And what happens is that out of the plaquettes in this lattice, you get an effective model that is totally different from the Icing model. It's called the XY model. And so you get a phase diagram that is based on the XY model rather than the Icing model. So you get all this really interesting emergent physics, and you can see topological phenomena such as topological phase transitions, Berezinski-Kosterlitz-Thouless phase transitions, which we identified, and vortices and anti-vortices. And so we were actually able to trace out a portion of the phase diagram near this topological phase transition. And our results agreed with the state-of-the-art classical simulation, which is based on path integral quantum Monte Carlo. And in this paper, again, we didn't study which one was faster. But then in a more recent paper, we took a closer look with the new lower noise D-Wave processors and actually compared the efficiency of the simulation between classical and quantum methods. So it's actually really difficult to get a handle on what's going on performance-wise in the quantum computer, because often when the quantum fluctuations are large, the relaxation is extremely fast. So basically, by the time you look at it, it's already finished. And so what we did in this experiment was we sort of tied the system into a topological knot. And I'll just go back. You can see at the top and bottom of the middle figure, the system is periodic, and you get all these arrows pointing all over the place. This is kind of an XY vector field. It doesn't really exist, but it exists in an effective model. And so we can actually set up an initial condition where this vector field is twisted in a topological obstruction, like a Mobius strip. And at equilibrium, the system is going to unwind itself and into a regular untwisted strip. So you have these illustrative pictures. And by doing this, by tying this system up into a topological obstruction to begin with, we're actually able to slow down the simulation enough that we can observe it. And you can see the quantum and classical simulations here compared in microseconds. And qualitatively, they converge to the same equilibrium value regardless of their initial configuration, except the quantum simulation here is about 3 million times faster. And this is a very efficient path integral Monte Carlo implementation on a single CPU core. So this is not quantum supremacy, but it's actually an interesting and relevant application that people have studied before. So it's not just a computer simulating itself. We're programming it to do something that it doesn't want to do normally. So we see also, in addition to this large constant factor speedup, we see a scaling advantage in both temperature and system size. Depending on whether you come from a computer science background or more of a physics background, you might be more interested in temperature or system size as a parameter. I personally feel that temperature is more relevant in this particular application. And you can see that the quantum annealing simulation, QA, and the path integral Monte Carlo simulation both slow down as you lower the temperature. But the quantum simulation slows down a lot less. And so you get a scaling advantage as the system gets colder and colder, which means that the quantum fluctuations become more and more significant. You also see a scaling advantage in system size, which means that as these simulations become larger, we can expect our computational advantage to grow. So I like to say that this is a real-world application as long as you believe that people who study quantum condensed matter physics live in the real world. And we saw up to 3 million times speed up versus a CPU core. And most importantly, I haven't gotten into the details of this, but most importantly, this is important evidence of something that a lot of people didn't believe was possible. So under certain conditions, there's provably no speed up available in this sort of simulation. So what we did was we showed that these conditions do not apply in this realistic situation. So as I said at the beginning, we're at a really interesting point in time. Over the past 10 years, I've been at D-Wave for 8 years. So over the past 10 years, we've gone from 128 qubits to over 5,000 qubits. So that's about a 50 times improvement in the number of qubits, along with all sorts of other parametric improvements. And so this sort of exponential growth that we're seeing in the quantum computing field right now is not just a myth, and it's not just an unrealistic projection. It's really happening. And so we've shown speed up over classical heuristics in crafted benchmarks. I've just shown you speed up in physics problems that are of real interest. And now we're at the point where customers are interested and they want to leverage these processors in solving their industrial applications. So I'm not going to pretend that these simulations are the same as most industrial applications. What we have is essentially an oracle for sampling low energy states of an Icing model. And so that is NP hard, it's NP complete. But it also is not in and of itself what most people are interested in doing with a computer, let alone a quantum computer. So for a long, long time, probably forever, real-world applications for business are going to be based on hybrid methods. So what we expect is that there's going to be a compute core that is performed by the quantum processor, and on either end of it, or probably in a loop, there's pre-processing, post-processing, and all sorts of parsing of the information that allows the hybrid method to refine solutions. So this allows us to get up to huge numbers of variables. We have on our online system a hybrid solver that's capable of handling up to 1 million variables. And we also have applications or hybrid methods that go out of the binary space. So your spins are not just up or down. With the hybrid methods, we can implement discrete variables rather than just binary variables. So this is going to be key to business applications. So just to wrap up, I've described some recent experiments in quantum simulation using D-Wave processors. And these simulation tasks really get at what's going on inside the core of the quantum annealing method. So this is really hard to visualize or get a good look at with optimization problems or black box optimization where you see what goes in and you know why. So we've actually managed to improve iteration and all sorts of things that we know about the processor by studying these quantum simulations. So this isn't yet a real-world application for most people, but it is very interesting to a lot of physicists. And to expand the interest, we're going to have to go to hybrid methods, and this is the path to business application. So thanks for your time.
Well, thank you very much for your talk and the news from D-Wave. I'm sure that there will be lots of applications. You can't hear me? Okay. Can you hear me? Well, I turn it on and off. Maybe it helps.
Oh, sorry. Yeah, I hear you now.
Okay, maybe it's your speaker. So I'm sure that D-Wave has a big future, as there are lots of these applications, connected to all kinds of difficult optimization problems. But as you said, what you have is just a fast quantum sampling. And for people who are more in computer science, just to let them understand better what is happening, you may say, well, we have simulated annealing, which has been used as one of the best methods for really optimization large scale, but now we are doing that in a quantum way, right? Is that a short summary of what D-Wave is
exactly
doing? Right? So this helps us to understand what kind of problems you can formulate and in which areas D-Wave may be really very helpful. And it's not only physics, but lots of other optimization problems. So my question is basically, except for physics, you've mentioned a few applications like Volkswagen and other companies. Have you made any tests on this classical optimization problems? Because when you go to conferences, let's say genetic algorithm people, right? They always have these benchmark problems that they will use for tests of different techniques. Of genetic or evolutionary algorithms. Has D-Wave been applied to some of these problems so that these guys in optimization will be more convinced to go into quantum business?
Yes. So for this kind of standard benchmark set, these have generally been benchmarked against the hybrid service. So this is using a combination of classical and quantum methods. So these can handle the really big problems that don't fit naturally on the D-Wave processor. And with that, we've had a lot of success. But that's the hybrid solver service that D-Wave has online has only been on for about a year and a half. So this is quite new.
Well, one of the big problems is of course, or most complex, is the optimization of the all kinds of microprocessor elements, etc., where there are now billions of elements and lots of constraints. So can you handle constraints in this kind of applications too?
Yeah. So if you don't use a hybrid method, you need to rephrase constraints as energy penalties, obviously, right, because the whole thing is minimizing the energy. So, how well you can do this depends on the specific application. Of course, if you have hybrid methods, then you can implement constraints in different and creative ways.
Well, you've mentioned also that, you have sometimes very fast relaxation time, but in simulated annealing, when you have a fast relaxation, that usually means that your temperature goes down too quickly, and so you're getting poor answers, right? So you have to slow it down somehow.
Well, yeah, I would say this becomes non-ergodic at this point. Right. What I mean by fast relaxation being a problem is that the most important part of the computation is where quantum and classical terms interact at relatively equal energy scales. And when this happens, we find that the dynamics are very fast compared to the annealing and readout control of the processor. So basically, our control of the processor is slower than the dynamics of the processor. So this can present all sorts of difficulties in benchmarking that have come up in many studies, where you make the annealing faster and faster and faster, but the results look the same because you're just observing it too slowly, or you're controlling it too slowly.
Okay, so that basically answers the question that we have in the chat. Does adjusting annealing time influence the performance of the simulation, right?
It influences the performance in many different ways. Some are desired and some are not desired. If you anneal very, very fast, then you can. We have evidence that you can decouple yourself from the environment and essentially behave in a closed system, which is usually what you want in a quantum simulation. Although open system quantum simulations are also very interesting. But also annealing slower allows you to often reach thermal equilibrium more accurately.
Mm. Okay, well, so I don't see any more remarks in our chat. So let me thank you again very much for this interesting talk, and we look forward for more quantum computing. I mean, the quantum computing and AI are the two most interesting but also influential now breakthroughs in science, I would say. And everybody is excited. And as you know, in Europe now, people have all these large-scale 1 billion euro projects in quantum area, not just quantum computing. So we can expect some interesting progress in recent years. Well, thank you very much once more. And just to finish, I would like to invite you to the network area. And mention that tomorrow and on Friday, there will be all kinds of workshops delivered by the System Biology Institute. So you can hear about the Garuda stuff, the Poznań Supercomputing and Networking Center, Huawei, ICM, University of Warsaw, and the Lenovo company. So please sign up for the workshops that have been prepared for the conference. Thank you.